As I said earlier, the purpose of this course is to examine carefully the underlying concepts of the various constructs and capabilities of programming languages. We will also evaluate these features focusing on their impact on the software development process, including maintenance. To do this, we need a set of evaluation criteria. Such a list of criteria is necessarily controversial because it is difficult to get even two computer scientists to agree on the value of some given language characteristics relative to others. In spite of these differences, most would agree that the criteria discussed in the following sections are important. One of the most important criteria for judging a programming language is the ease with which programs can be written and understood. Before 1970, software development was largely thought of in terms of writing code. The primary positive characteristics of programming languages was efficiency. Language constructs were designed more from the point of view of the computer than the computer user. In the 1970s, however, the software lifecycle concept was developed. Coding was relegated to a much smaller role, and maintenance was recognized as a major part of the cycle, particularly in terms of cost. Because ease of maintenance is determined in large part by the readability of programs, readability became an important measure in the quality of the programs and the programming language. This was an important juncture in the evolution of programming languages. There was a distinct crossover from the focus on machine orientation to a focus on human orientation. Readability must be considered in the context of the problem domain. For example, if a program that describes a computation is written in a language not designed for such use, the program may be unnatural and convoluted, making it unusually difficult to read. The following discussions present the various aspects of readability for a computer programming language. The overall simplicity of a programming language strongly affects its readability. A language with a large number of basic constructs is more difficult to learn than one with a smaller number. Programmers who must use a large language often learn a subset of the language and ignore others. Readability problems occur when the program's author has learned a different subset from the subset with which the reader is familiar. A second complicating characteristic of a programming language is feature multiplicity. That is, having more than one way to accomplish a particular operation. For example, in Java, a user can increment a single integer variable in 4 different ways. The third potential problem is operator overloading, in which a single operator symbol has more than one meaning. Although this is often useful, it can lead to reduced readability if users are allowed to create their own overloading and do not do it sensibly. For example, it is clearly acceptable to overload the plus operator to use it for both integer and floating point arithmetic. In fact, this overloading simplifies a language by reducing the number of operators. However, suppose the programmer defined the plus operator used between single dimensioned array operands to mean the sum of all elements in both arrays. Because the usual meaning of vector addition is quite different from this, it would make the program more confusing for both the author and the program's readers. And even a more extreme example of program confusion would be a user defining plus between 2 vector operands to mean the difference between their respective first elements. Simplicity in languages can of course be carried too far. For example, the form and meaning of most assembly language statements are models of simplicity. as you can see when you consider the statements that we talk about in the next section. This very simplicity, however, makes assembly language programs less readable. Because they lack more complex control structures, program structure is less obvious. Because the statements are simple, far more of them are required than in an equivalent program in a high-level language. These same arguments apply to the less extreme case in high-level languages with inadequate control structures and data structure and constructs. Orthogonality has proven to be one of the most difficult concepts to teach about computer science languages. So let's try to attack it from various perspectives. First of all, let me make it clear that the concept of property of orthogonality changes based upon the way in which it is used. In some sense, you might say it's a bit polymorphic in its behavior. But in a more very general sense, orthogonality is a property that means changing A does not change B. That is to say that things are independent of each other or loosely or not coupled at all. So from a system standpoint, a radio is an orthogonal system because changing the station does not change the volume, and changing the volume does not change the station. A non-orthogonal system would be like a helicopter, where changing the speed can change the direction and vice versa. From the standpoint of languages, orthogonality means a feature is bounded with no exceptions or restrictions. A non-orthogonal feature in English is I before E, except after C. An orthogonal feature of English is that all sentences must end in some kind of punctuation, no exceptions. From the standpoint of programming languages, orthogonality means that every feature is compatible with every other feature. An orthogonal feature in C++ is that pointers can point to any data structures. Pointers can even point to pointers. A non-orthogonal feature in C++ is that any data structure can be passed to a function by value, except an array. So from the standpoint of all of these various uses of the word orthogonality, we can say that orthogonality in its purest sense in programming languages means that the language has a relatively small set of constructs that can be combined in a relatively small number of ways, and all of those ways are both legal and meaningful. Another aspect of programming languages that adds to its readability is data types. Now, if we were to program in a language that did not have a Boolean data type, one would have to write the following sentence, which is vague and not easily understood, not easily read. However, if rewritten in a language that did have Boolean variables, this statement could be written in the second form, which was very clear and straightforward. The meaning of this statement is perfectly clear. Another example is if we were working with a language that had an enum data type, we could define a user-defined type called day, and then define today and tomorrow, and this would be much more readable and much more clear to the reader. Syntax design is another important aspect of readability of a programming language. The syntax or form of the elements of a language have significant effect on the readability of its programs. The following are some examples of syntactic design choices that affect readability. First, special words. Program appearance and thus program readability are strongly influenced by the forms of the language's special words. For example, while, class, for, do in C++. Especially important is the method of forming compound statements or statement groups, primarily in control constructs. Some languages have used matching pairs of special words or symbols to form groups. C and its descendants use braces to specify compound statements. All of these languages suffer because statement groups are always terminated in the same way, which makes it difficult to determine which group is being ended when an end or right brace appears. Fortran 95 and Ada make this clear by using a distinct closing syntax for each type of statement group. For example, Ada uses end if to terminate a selection construct and end loop to terminate a loop construct. This is an example of the conflict between simplicity that results in fewer reserved words as in C++ and the greater readability that can result from using more reserved words as Ada. Another important issue is whether the special words of a language can be used as names for program variables. If so, the resulting programs can be very confusing. For example, in Fortran 95, special words such as do and end are legal variable names. So the appearance of these words in a program may or may not connote something special. Another consideration, forms and meanings of keywords. Designing statements so that their appearance at least partially indicates their purpose is an obvious aid to readability. Semantics or meaning should follow directly from syntax or form. In some cases, this principle is violated by two language constructs that are identical or similar in appearance but have different meanings, depending on perhaps their context. In C, for example, the meaning of the reserved word static depends upon the context of its appearance. If used in the definition of a variable inside a function, it means the variable is created at compile time. If used in the definition of a variable that is outside all functions, it means that a variable is visible only in the file in which its definition appears, that it is not exported from the file.